Welcome back, everybody. This is AP Chemistry. We're in Unit 8 and Section 2, taking a look at something called the Henderson-Hasselbalch equation. Now, here's the cool part, guys. I showed you in the last section, taking a look at the effect of buffers and everything, and how they would absorb up or eat up some of the hydrogens or hydroxides of different solutions. And that does involve doing basically two sets of equations with it. It's kind of a cumbersome type of thing. The Henderson-Hasselbalch equation, I said that you guys are going to like this because it's a very simple process to achieve the exact same thing. So this is basically what's going on with that. And taking a look at the pH is going to be a function of that pKa plus the log of your base over your acid. So we always write it in this particular route, but let's take a look and let me write this in a different way that I think is going to be a little bit easier for you. The pH is going to be a function of the pKa. Okay, remember what that is with the pKa part, and we'll run through those. And let's see, and that's going to add in the log of the concentration of your base over the concentration of your acid. Okay, so that's what we're talking about here. That's the conjugate base of your acid in that regard. Okay, so that is your equation. You're going to find the Henderson-Hasselbalch is going to be a faster way of doing all these. I'm going to show you the old way, okay, the one from section 2 first, just so you see how all this is really working. We see that we've got lactic acid, which is a weak acid, and we're going to add in sodium lactate. Okay, what's going to happen is this lactate is going to eat up some of those hydrogens in there, and so in the last unit we just said, okay, we have the C3H5O3 is going to dissociate my hydrogen ions and my C3H5O3. Now, my major species, if I was going to be looking at it that way, would be that lactic acid. I'll just abbreviate it La. We do have the water. Okay, that's not going to really do anything for us. We have the sodium from my sodium lactate. Okay, remember the sodium doesn't do anything for us. And then we have the lactate. Okay, and that since I have the lactate here, he is going to be absorbing some of those hydrogens that's going to be used up along the way. Okay, so those are going to be our major players in there. And so if I track all of these things along the way, I started with a 0.75. We're going to lose some of that. He's going to gain some of that. We had a starting introduction of 0.25 molar solution of this as well, 0.25, and he's going to eat up some of those. Okay, so my Ka was a 1.4 times 10 to the negative 4. That equals my X times the 0.25 plus X over 0.75 minus X. Okay, again, these are small values. I can disregard, multiply both sides by 0.75, then divide by 0.25. I end up with X equaling 4.2 times 10 to the negative 4, and I get a pH is going to equal 3.38. Okay, so this is what we did with regards to the more traditional way from section 1. Now let's use the Henderson-Hasselbalch method as the prompt says. And remember, if the AP board asks for this question, they'll say they'll ask for it specifically using this equation or this method. So go back to my equation. I see that the Henderson-Hasselbalch tells me that I have the pH is going to equal the pKa plus the log of the concentration of my base over the concentration of my acid. And you might stop with all of these different things that's going on. It's like, wait a minute, what is this pKa thing again? What is that? Well, remember, when we're solving for the pH scale of anything, remember that the pKa equals the negative log of your Ka. Okay? Oh, all of a sudden, things start falling together. Because what is my pKa? Or, sorry, what is my Ka? Well, my pH is going to be the negative log of my 1.4 times 10 to the negative 4. Okay, now we're going to add that in my equation. We're going to add that to the log of the concentration of my base. And what was the concentration of my base again? Where do we find that? Oh, we find it from the problem itself. I have this is my base, the 0.25, and what did I have for my acid? I have the 0.75. Okay, so if I take a look at that, I end up with pH equals the negative, or sorry, the pH ends up being 3.85 plus, and then the log of this ends up being a negative 0.48. Okay, so my pH ends up being 3.37. Much faster, much easier on the mind. It's not exactly, but it's because of kind of rounding and things like that that we see that those values are very similar to one another. Okay, so a simpler way of doing it, just keeping your wits about you in terms of how do we derive those things. So here's another prompt, and again, if the College Board asks for the Henderson-Hasselbalch, then you'll want to do it that way. Now, this one is saying that we found the pH or we want to find the pH when we have a 0.5 molar and a 0.5 molar, again, of the acetates, acetic acid and the acetates. So if I'm going to use this method, we would see the pH equals the pKa plus the log of my base concentration, those should be brackets, over my acid concentration. Okay, I know I keep rewriting it, but it's just good practice to document what we're doing here. All right. Now, again, what is pKa? Well, pH equals the negative log of Ka plus the log of my base over my acid. Okay, what was the base over my acid? Well, I saw that I had a 0.5 molar. Okay, and then I have a 0.5 molar. Okay, so if I just do that, well, that's a log of 1, which is 0, and then the pH would be the negative log of my Ka value. Okay, so that's pretty straightforward. We're just going to be absorbing those things in there. Okay, so if I do that, that ends up being, this was a 1.8 times 10 to the negative 5. All right, so that's all I'm going to be doing. Now, I want to more address this second part, okay, because we're adding in 0.01 moles to this. So remember what that does. That's going to eat up some of those hydrogens. What does that do? Okay, if I was going to just address this in my Henderson-Hasselbalch, well, remember what's happening. The pH is the negative log of the 1.8 times 10 to the negative 5 plus the log of my base over my acid. So if I'm going to be adding some base in here, what happens? Well, that adds to this, doesn't it? So I'm going to be taking my 0.5 plus my 0.01 moles, and it's going to be eating up some of these, the 0.5 minus the 0.01 moles. Okay, now you might be wondering, why am I just saying moles all of a sudden? We had 1 liter, we'll assume 1 liter when we have this, and so that's how I knew how many moles I had to begin with. And so I have a pH that's going to equal 4.74 plus the log of this, so a 0.51 and a 0.49, that will give me a plus a 0.017. Okay, so now if I add that all up, the pH is going to be a 4.76. So that added to and brought it up, which is exactly what we would predict, because I added a base that will bring the pH up a little bit from the original, which was 4.74. Okay, that's what I would get on this side, is a 4.74. Then I added the base in there. Okay, so we're going to take a look at one more example of using this, and that should set you up to do the last of the problems as we go. So calculate the pH of a solution when we have 0.10 moles of an acid this time added to ammonia, and we have also ammonium chloride. Notice it's 1 liter of each, so these are going to be actually a 0.25 moles and a 0.40 moles, just like we did in the last problem. Okay, using the Henderson-Hasselbalch, we'll go the pH equals the pKa. Remember, that is the negative log of the Ka. and we're going to add that to the log of my base. Well, now remember what's happening here. I'm adding an acid. That's going to eat up some of my base, isn't it? Okay, so who's my base in this? Well, my base is my ammonia, okay, because that's going to be accepting in the hydrogen. And so I have 0.25 plus my let's see, how many moles? I had 1.1 moles of, let's see, I'm sorry. I'm going to be, actually, this is going to be my base. He's going to lose the 0.1 moles here. And so then I have also my 0.40 plus my 0.1 moles from my acid. Okay, because the acid side, this is going to be gaining that. And so I end up with plugging my values in. We saw that I ended up with a 9.25 plus a minus 0.52. And so my pH ends up being 8.73. Okay, so that's what we've got with that. Now, if I wanted to work this in reverse, because they gave me some values, and so the question is, wait, how did I get my value for my Ka? Remember, we saw this, my Ka times my Kb equals 1 times 10 to the negative 14. And so if I plug in the value 1.8 times 10 to the negative 5 here, my Ka ends up being 5.56 times 10 to the negative 9. Okay, and so that's the value that I put in right there. If I went with my 1.8 times 10 to the negative 5, you'd be solving for a POH. Okay, then you'd have to subtract that from 14 to get my pH from there. So that's just clarifying a little bit of that, and I think you've got enough to be able to do your Henderson-Hasselbalch.